For centuries, the Great Wall of China has stood as one of humanity's most iconic achievements. A massive ribbon of stone and earth stretching across mountains, deserts, and valleys, winding its way for more than 13,000 miles. Because of its sheer length and historical grandeur, a popular belief emerged sometime in the 20th century. The Great Wall is the only man-made structure visible from space with the naked eye. The idea sounded poetic, a human monument so vast it could be seen by astronauts orbiting hundreds of kilometers above Earth. School textbooks repeated it, teachers quoted it with pride, even trivia books printed it as fact. It was a myth that inspired awe. If humans could build something visible from space, what greater proof of our collective power and endurance could there be? But when the first astronauts actually went to space and looked down upon Earth, they discovered something far less romantic and far more surprising. The Great Wall, despite being one of the longest structures ever built by human hands, is incredibly difficult to spot from orbit. In fact, it's nearly invisible without the aid of cameras, zoom lenses, or perfect atmospheric conditions. The reality is that cities, highways, airports, and farmland patterns are far easier to see than the Great Wall itself. The exact origin of the myth is unclear, but historians and space experts trace it back at least to the early 20th century. In 1938, British author Richard Halliburton published a book titled Second Book of Marvels, in which he boldly claimed that the Great Wall of China was the only man-made object visible from the moon. This wasn't based on scientific evidence. In fact, no one had been to space yet. It was simply an assumption, perhaps inspired by the wall's legendary length and historical significance. Over time, this assumption got repeated so often that it hardened into fact. When spaceflight became a reality in the 1960s, many expected astronauts to confirm what books and teachers had been saying for decades. But instead, they returned with a shocking correction. They couldn't see it. Yet by then, the myth was already so embedded in popular culture that it took years to undo. So, what can astronauts really see from space with the naked eye? At an altitude of about 400 kilometers, the orbit of the International Space Station, astronauts can easily see large landmasses, coastlines, deserts, and major rivers. Human-made features that stand out are usually high-contrast objects like city lights at night, massive airports, long highways, or sprawling agricultural patterns. The Great Wall, however, is only a few meters wide and made of materials that blend in with the natural landscape: stone, earth, and wood. From space, it looks nearly the same color as the surrounding mountains and desert, making it camouflage itself into the terrain. Astronaut William Pogue of Skylab, 1973-74, admitted that he thought he had spotted the wall, but when he compared his notes to photos, he realized he had been looking at a river. In 2003, China's first astronaut, Yang Liwei, was asked whether he saw the wall from space. His reply was short: no. That moment struck a chord across China because it contradicted a source of national pride. Later, high-resolution cameras confirmed what the astronauts were saying. The wall is visible in some photographs taken from orbit, but only under perfect conditions with zoom lenses, not with the unaided human eye. The misunderstanding comes from confusing length with visibility. While the Great Wall is thousands of miles long, it is very narrow, often less than 30 feet wide. From hundreds of kilometers up, it's like trying to spot a single human hair stretched across a basketball. The color of the wall doesn't help either. It matches the earth around it. A shiny metal bridge or bright concrete highway has more contrast against nature than the ancient, weathered stones of the wall. To put it in perspective, astronauts have reported spotting runways of airports more easily than the Great Wall, even though airports are much smaller in total size. Why? Because long, flat, black runways contrast sharply against surrounding landscapes. It's not size alone that makes something visible. It's the combination of width, color, and contrast. In the early 2000s, NASA released satellite images proving the difficulty of spotting the wall. Astronaut Leroy Chiao, who commanded the International Space Station in 2014, managed to capture one of the clearest photographs of the Great Wall from orbit, but he did so with a camera and a powerful lens. Even then, the wall was just a faint line blending with the landscape. Chow admitted that he wasn't sure he was photographing the right structure until experts confirmed it later. His conclusion was simple: with the naked eye, spotting the Great Wall is next to impossible. This evidence finally helped debunk the myth on a global level. Textbooks slowly updated their facts. Space agencies began clarifying the misconception in their outreach programs. Yet, despite all this, many people around the world still casually repeat the old claim, a testament to how stubborn myths can be once they become part of culture. Part of the reason this myth refuses to die is because it's emotionally satisfying. The Great Wall is one of the most magnificent human achievements, and the thought that it could be seen from space feels like a poetic tribute to the effort of millions of workers who built it. It's more than a wall. It's a symbol of endurance, defense, and civilization. To say that it's visible from space makes it sound even more epic. Humans love stories that make us feel small in the grand scheme of the universe, while reminding us of our power to leave marks on Earth. Unfortunately, science doesn't always cooperate with poetry. The truth may be less glamorous, but it's no less fascinating. The things most visible from space aren't necessarily our greatest monuments, but the glowing lights of our cities, the geometric grids of our farms, and the expanding scars of deforestation. In a way, this is even more humbling. It shows how much we reshape our planet in ways we often don't notice from the ground. This myth isn't just about the Great Wall. It teaches us something crucial about human belief and science. We often accept claims because they feel right, not because they are proven. For decades, the Great Wall myth persisted simply because it sounded logical and inspiring. But when tested against reality, through direct observation and evidence, it crumbled. This is how science works. Not by reinforcing what we want to be true, but by uncovering what is true. And perhaps there's an even greater irony here. Even if the Great Wall isn't visible from space, the story of how it fooled generations reminds us of our tendency to romanticize knowledge. It encourages us to keep asking questions, to challenge what we're told, and to look deeper than the surface. So, is the Great Wall of China visible from space? The simple answer: not with the naked eye. It's an incredible feat of engineering, but space doesn't care about legends or poetry. What astronauts actually see from orbit are coastlines, rivers, cities, and airports, not thin stone walls blending into the terrain. Yet the Great Wall remains extraordinary, not because it's visible from space, but because it represents human perseverance and ambition. The next time someone repeats this myth, you'll know the truth, and perhaps you'll appreciate the wall even more, not for what it looks like from above, but for what it means down here on Earth. When you picture space, what do you hear? For many people, the answer is simple: nothing at all. Movies often reinforce this image, showing explosions, rocket battles, and vast stretches of black emptiness followed by complete silence. Science teachers echo the same statement in classrooms. Space is a vacuum, and in a vacuum, there is no sound. The idea has become so popular that it feels almost unquestionable. If you were to step outside your spacecraft and shout, your voice would vanish into absolute silence. But is space really silent? The truth is far more fascinating, and it changes depending on how you define sound. Yes, space is mostly a vacuum, which means there are no air molecules to carry sound waves like we experience on Earth. But silence is not the whole story. Space is filled with particles, plasma waves, electromagnetic vibrations, and energy fields that can, in fact, be translated into sound. In other words, space has its own kind of music. We just need the right instruments to hear it. The myth of silence in space is rooted in basic physics. On Earth, sound travels as a mechanical wave. Molecules bump into each other, carrying vibrations through the air, water, or solid material. In the vacuum of space, there are very few molecules around, so there's no medium for sound waves to move through. If you took off your helmet and tried to scream in open space, no one would hear you. Your vocal cords would vibrate, but with nothing to carry those vibrations, the sound would simply stop. This is true, but it's only half the story. Because while sound as we understand it can't travel in a vacuum, space isn't completely empty. It's filled with gas clouds, plasma, dust, and radiation. These can carry vibrations of their own, which scientists can measure and, using instruments, translate into sounds we can actually hear. Over the past few decades, space agencies like NASA and ESA have captured some of the eeriest and most fascinating sounds from space. These aren't sound waves in the traditional sense. They're electromagnetic signals, plasma oscillations, or wave-particle interactions that can be converted into audio frequencies for human ears. For example, the Voyager spacecraft, which has been traveling through space since the 1970s, recorded plasma waves in the space environment around planets like Jupiter and Saturn. When converted into sound, these waves create haunting, ghostly tones, long hums, crackles, and deep echoes that sound like the soundtrack of a sci-fi horror movie. Another example comes from black holes. In 2022, NASA released an audio clip of sound waves detected from a black hole in the Perseus galaxy cluster. The black hole was generating pressure waves that rippled through surrounding hot gas. By adjusting the frequencies into the human hearing range, scientists revealed a chilling audio track, something like a cosmic howl echoing across millions of light years. These discoveries prove that while you might not hear space with your ears, the universe is vibrating with activity that we can translate into sound. Perhaps the most surprising fact is that even our sun sings. The sun constantly produces vibrations as its outer layers bubble, churn, and move. These vibrations travel as pressure waves through the solar plasma, much like sound waves moving through air. Scientists studying the sun use a field called helioseismology, the study of these waves, to understand what's happening inside the sun. When translated into audio, the sun's song is a series of rhythmic pulses, almost like a drumbeat or a low-frequency hum. It's not silence at all. It's an ongoing, booming concert of nuclear fusion and plasma motion. Imagine, every second of every day, our star is vibrating with energy, playing music across the solar system that we can't hear without scientific instruments. Another reason the space is silent myth sticks around is because people forget that astronauts don't live in open vacuum. They live inside spacecraft, which are very noisy places. Inside the International Space Station, astronauts often describe the constant hum of fans, pumps, and machinery that keep the life support systems running. Air circulation systems, computers, and power generators all create a background noise that astronauts get so used to they sometimes can't sleep without it. Chris Hadfield, a Canadian astronaut, once said that the ISS sounds a bit like being inside a humming refrigerator, not exactly silent. So while space outside is empty, the human experience of space is actually filled with mechanical noise. Movies often dramatize the idea of silence in space by showing astronauts drifting away, their screams swallowed instantly into nothing. While it's true that no one would hear you in the vacuum, you would still hear something, yourself. Sound doesn't need air, it just needs a medium. Inside your body, there's plenty of medium, tissue, bone, and fluid. So if you tried to shout in space, your voice wouldn't travel outside your body, but you would hear the muffled vibrations through your skull. You'd literally hear yourself from the inside. It wouldn't save you from suffocation, but it's an eerie reminder that silence is never absolute. Hollywood has played a huge role in spreading this myth. Movies like Star Wars are famous for space battles filled with booming explosions and roaring engines, sounds that would be impossible in a real vacuum. But here's the twist. Even though it's scientifically wrong, audiences like it. Imagine watching a massive space battle in total silence. It would feel flat and anticlimactic. Sound designers add explosions and rumbles to make it emotionally powerful, not scientifically accurate. On the other hand, some movies have dared to depict space more realistically. In 2001, A Space Odyssey, 1968, director Stanley Kubrick portrayed space scenes with silence, capturing the eerie emptiness of the cosmos. More recently, the movie Gravity, 2013, mixed silence with vibrations. You don't hear explosions directly, but you hear muffled booms through what astronauts might feel in their suits or spacecraft. These creative choices reflect a growing awareness of the reality of space's silence. So, if space isn't truly silent, what is it? Think of it as a grand cosmic symphony, but one that humans can't hear without help. Every star, planet, and galaxy is vibrating, pulsing, or releasing energy in some form. The problem is that most of these sounds exist in frequencies outside our hearing range, or as electromagnetic signals instead of pressure waves. Scientists use technology to translate them, and when they do, the results are astonishing. Imagine hearing the deep rumble of Jupiter's magnetosphere, the eerie whistles of solar winds, or the ultrasonic thrum of a pulsar spinning 700 times per second. These sounds are real, but hidden. A universe constantly alive with noise, waiting to be decoded. The myth of complete silence in space is partly true, but dangerously oversimplified. It reminds us of the limits of human senses. Just because we can't hear something doesn't mean it isn't there. The universe speaks in frequencies we can't naturally detect, but with science we can tune into those hidden voices. This changes the way we see space, not as a silent void, but as a living, vibrating, dynamic environment full of hidden rhythms. In a way, this is inspiring. It tells us that silence itself is a human illusion. The cosmos has always been speaking. We are just learning how to listen. So, is space silent? Yes and no. If you floated unprotected in the vacuum, your voice wouldn't travel. In that sense, silence exists. But space is far from quiet. The sun hums, planets roar, black holes howl, and cosmic plasma crackles with strange vibrations. Inside spacecraft, the noise of life support machines fills the air. And through the ears of our instruments, the universe reveals itself as a never-ending concert of energy and motion. The myth of silence makes space seem empty, but the truth is much richer. Space is alive with sound, just not the kind we're used to. If you ask a child to draw the sun, chances are they'll grab a yellow crayon. From storybooks to weather icons, the sun is almost always depicted as a glowing golden circle. Even adults casually describe sunny days as bright and yellow. But here's the surprising truth. The sun is not actually yellow. It is in fact white. So why does it look yellow from Earth? The answer lies in the way our atmosphere plays tricks on our eyes. The sun emits light across the full spectrum of visible wavelengths. When all those wavelengths are combined, the result is pure white light. If you were standing outside Earth's atmosphere, for example aboard the International Space Station, the sun would appear as a brilliant white star, not yellow or orange. On Earth, however, sunlight has to pass through our atmosphere before it reaches our eyes. Molecules in the atmosphere scatter shorter wavelengths, blue and violet light, more effectively than longer wavelengths, red and yellow. That's why the sky appears blue. As sunlight is scattered, the remaining light that reaches our eyes has more yellow and red tones. This gives the sun its familiar golden appearance when viewed from the ground. The same principle explains why sunsets and sunrises often appear deep red or orange. During these times, sunlight travels through a thicker slice of atmosphere before reaching us. More of the shorter blue wavelengths are scattered out, leaving the longer red wavelengths to dominate. This creates those fiery skies we find so beautiful at dusk and dawn. But if you were in space, orbiting above Earth's atmosphere, the sun would always look blindingly white, no matter the time of day. The image of a yellow sun has been burned into human culture for centuries. Ancient civilizations often associated it with gold, fire, and divinity. In art and mythology, the sun was depicted as golden because that color symbolized life, warmth, and prosperity. This cultural tradition stuck even after science revealed its true color. Even today, weather forecasts use yellow suns on graphics to symbolize clear skies, and kids' books show smiling yellow faces in the sky. The yellow sun myth isn't harmful, but it does show how deeply culture and perception can shape what we think is reality. The sun isn't yellow, it's white. The golden glow we see is just an atmospheric illusion, a side effect of how light interacts with Earth's air. If you could view it from space, you'd see it in its true color, a brilliant white star, no different from the countless others scattered across the galaxy. When we watch astronauts float gracefully through the International Space Station, it's easy to assume that space has no gravity. After all, they're weightless, drifting from wall to wall like balloons. Teachers often reinforce the idea by saying things like, space is a place without gravity. But this is a huge misconception. Gravity exists everywhere in the universe, and without it, planets, stars, and galaxies wouldn't even exist. So why do astronauts look weightless? The answer lies in the concept of free fall. The International Space Station orbits Earth at about 400 kilometers above the surface. At that height, Earth's gravity is still about 90% as strong as it is on the ground. If gravity suddenly disappeared, the ISS would shoot off into space in a straight line. Instead, gravity constantly pulls it downward. But the ISS is also moving sideways at about 28,000 kilometers per hour. This sideways speed is so fast that as it falls, Earth curves away beneath it. The result, the ISS keeps falling around Earth without hitting it. Astronauts inside are falling at the same rate as the spacecraft, which creates the sensation of weightlessness. They aren't beyond gravity, they're riding it. When we watch astronauts float gracefully through the International Space Station, it's easy to assume that space has no gravity. After all, they're weightless, drifting from wall to wall like balloons. Teachers often reinforce the idea by saying things like, space is a place without gravity. But this is a huge misconception. Gravity exists everywhere in the universe, and without it, planets, stars, and galaxies wouldn't even exist. So why do astronauts look weightless? The answer lies in the concept of free fall. The International Space Station orbits Earth at about 400 kilometers above the surface. At that height, Earth's gravity is still about 90% as strong as it is on the ground. If gravity suddenly disappeared, the ISS would shoot off into space in a straight line. Instead, gravity constantly pulls it downward. But the ISS is also moving sideways at about 28,000 kilometers per hour. This sideways speed is so fast that as it falls, Earth curves away beneath it. The result, the ISS keeps falling around Earth without hitting it. Astronauts inside are falling at the same rate as the spacecraft, which creates the sensation of weightlessness. They aren't beyond gravity, they're riding it. Gravity doesn't stop at the edge of Earth's atmosphere. It stretches infinitely into space, though it weakens with distance. It's what holds the moon in orbit around Earth, Earth around the sun, and the sun around the center of the Milky Way galaxy. Without gravity, planets wouldn't form, stars wouldn't ignite, and galaxies wouldn't swirl. In fact, gravity is the architect of the cosmos, the invisible hand shaping everything we see in the night sky. The myth comes from the language we use. Terms like zero gravity or microgravity are often used to describe conditions in orbit. Technically, these phrases don't mean that gravity is gone. They mean that its effects are greatly reduced or balanced in such a way that objects appear weightless. Unfortunately, most people interpret them literally. Space is not gravity-free. Astronauts float because they are in a constant state of free fall around Earth, not because gravity has vanished. In fact, gravity is everywhere, quietly pulling, shaping, and sculpting the universe we live in. Few cosmic objects capture human imagination like black holes. In movies, they're often shown as terrifying whirlpools of destruction, sucking in entire planets, ships, and even light itself. The myth paints them as cosmic vacuum cleaners that indiscriminately devour everything around them. But the reality is both less dramatic and more fascinating. Black holes don't suck things in. They simply exert gravity, the same force that Earth and the Sun use to keep us in orbit. A black hole forms when a massive star collapses under its own gravity at the end of its life cycle. The collapse compresses the star's mass into an incredibly small volume, creating a region where gravity is so strong that not even light can escape. This boundary is called the event horizon. If you cross the event horizon, escape becomes impossible. But outside of it, gravity works just like it does anywhere else in the universe. The closer you are, the stronger the pull. The vacuum cleaner myth likely comes from the dramatic way black holes are depicted in fiction. Movies often show them pulling objects across space like a giant cosmic drain. In reality, if our sun were replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now. We wouldn't get sucked in. The only difference would be the absence of sunlight. Objects only get drawn into a black hole if they pass very close to it, within its strong gravitational influence. Otherwise, they orbit it like they would any other massive object. That said, black holes are still incredibly extreme. As you approach one, tidal forces can stretch objects into long strands in a process known as spaghettification. Gas and dust spiraling into a black hole form an accretion disk that glows brighter than entire galaxies due to intense heat and radiation. Jets of energy can shoot out at nearly the speed of light. These phenomena are awe-inspiring, but they're not the same as cosmic vacuuming. Part of the myth comes from our natural fear of the unknown. Black holes represent places where our usual understanding of physics breaks down. They're mysterious, invisible, and powerful, making them perfect for scary stories. But the truth is, black holes aren't roaming monsters. They're simply objects with very strong gravity, governed by the same laws of physics as everything else. Black holes don't suck everything around them. They only pull in matter that ventures too close to it. From a safe distance, they behave just like stars or planets of the same mass. Rather than cosmic vacuum cleaners, they're more like powerful engines that reshape their surroundings in strange and fascinating ways. For centuries, poets, dreamers, and storytellers have spoken of the dark side of the moon as if one entire half of Earth's celestial neighbor lives in eternal night. The phrase itself is so deeply rooted in popular culture that even music albums and movies have used it as a mysterious symbol. People imagine that half of the moon is always pitch black, unexplored, and forever hidden from the sun's light. But here's the truth. There is no permanent dark side of the moon. What we actually have is a far side of the moon, the hemisphere that always faces away from Earth because of a phenomenon called tidal locking. Both sides of the moon experience sunlight and darkness in equal measure during the lunar cycle. To understand why this myth became so powerful, we need to go back to how the moon orbits Earth. Billions of years ago, when the moon first formed after a giant collision between Earth and a Mars-sized object, it was spinning much faster. Over time, Earth's gravitational pull acted like a brake, slowing down the moon's rotation until its rotation period matched its orbital period. Today, the moon takes about 27.3 days to rotate once on its axis and the exact same amount of time to orbit Earth once. This perfect match is why we always see the same familiar face of the moon from Earth, the one with the man in the moon patterns of craters and Maria. The other half, the far side, remains invisible to us without the help of spacecraft. But invisible to Earth does not mean dark forever. It simply experiences day and night just like the side we see, with 2 weeks of daylight followed by 2 weeks of night. So why do people continue to believe in a dark side? One reason is linguistic confusion. Astronomers correctly call it the far side, but the popular imagination turned that into dark side. The term stuck because it sounded mysterious, almost magical. Before space exploration, nobody had ever seen images of the moon's hidden hemisphere, so it was easy for myths to grow. For example, science fiction writers love to describe alien bases or secret civilizations hiding on the dark side, as if it were a permanent shadowed land beyond human reach. When Pink Floyd released their legendary album, The Dark Side of the Moon, in 1973, the phrase gained an even stronger cultural foothold. Music lovers, not astronomers, ensured that dark side would forever be part of human vocabulary, even though it's scientifically inaccurate. The first real look at the moon's far side came in 1959 when the Soviet spacecraft Luna 3 photographed it. The images were grainy but revolutionary. They revealed a surface strikingly different from the side we know. Instead of vast, dark volcanic plains, Maria, the far side was covered in rugged mountains and heavily cratered highlands. For the first time, humanity realized that the moon was more complex than it appeared through a telescope. In 1968, during the Apollo 8 mission, American astronauts became the first humans to actually see the far side with their own eyes as they orbited the moon. They described the view as breathtaking, silent, and utterly alien. And yet, even then, popular newspapers continued calling it the dark side, fueling the myth. Let's get even more precise. At any given time, half of the moon's surface is illuminated by the sun, just like Earth. That half shifts as the moon rotates, meaning the far side also gets 2 weeks of sunlight during its lunar day. When Apollo astronauts orbited the moon, they observed this directly. As their spacecraft passed behind the moon, the far side sometimes glowed brightly under the sun. The only thing that makes it dark to us on Earth is that we can't see it without leaving our planet. In other words, the darkness is in our perception, not in the moon's reality. This myth isn't just an innocent mistake. It also shapes how people think about exploration. Believing in a permanent dark side makes the moon seem like a place of eternal mystery, when in fact it's a dynamic world that we've mapped in exquisite detail. Thanks to satellites like NASA's Lunar Reconnaissance Orbiter, we now have high-resolution images of every crater, ridge, and valley, both near side and far side. In fact, the far side has become an exciting destination for future missions. In 2019, China's Chang'e 4 mission made history by successfully landing a rover, Yutu-2, on the moon's far side. This was the first time humanity had touched down in that once mythical territory, proving that what was once considered dark and unreachable is now a part of scientific study. Another fascinating angle is how this myth affects our imagination of space life. Many conspiracy theories take advantage of the so-called dark side. You'll find stories online about secret alien bases, hidden Nazi outposts from World War II, or giant UFO hangars supposedly lurking in eternal shadow. Hollywood films and TV shows have borrowed this imagery countless times. But in truth, there are no permanent shadows covering half of the moon. The only places that stay in darkness are the floors of certain craters near the moon's poles, where the sun never rises above the horizon. These regions are scientifically fascinating because they may contain frozen water, an essential resource for future lunar colonies. But again, this is very different from saying half the moon never sees sunlight. Interestingly, psychology plays a role here too. Humans love mystery. Our minds are wired to romanticize the unknown. A far side that is just out of view but still normal and sunlit doesn't sound nearly as exciting as a dark side locked in shadow. By using the language of darkness, storytellers tap into our primal fears and curiosities. In ancient cultures, darkness was always associated with danger, secrets, and the supernatural. The myth of the moon's dark side fits neatly into that pattern, which is why it has survived even after astronauts and spacecraft proved it wrong. So, the next time you hear someone mention the dark side of the moon, you'll know better. There is no eternal shadow covering half of our closest neighbor. Both hemispheres bask in sunlight and plunge into night just as Earth does. What exists is a hidden side, hidden from us on Earth, but not from the universe. Busting this myth doesn't make the moon less fascinating, it makes it even more extraordinary. Because instead of imagining a lifeless, shadowed wasteland, we can now dream about exploring a terrain filled with mountains, craters, and maybe even resources that will help humanity build its future in space. In short, the myth of a permanent dark side is a powerful reminder of how language and culture can distort scientific truth. The far side is not a land of eternal night, but a world waiting for us to explore step by step, crater by crater. The darkness lies not on the moon, but in our outdated beliefs. If you ask most people to imagine astronauts floating in space, they'll immediately say, that's because there's no gravity up there. It seems logical. After all, the videos we see from the International Space Station show astronauts drifting effortlessly, water forming floating spheres, and objects hovering in the air as though gravity has completely vanished. But here's the surprising truth. Gravity never goes away. Even 400 kilometers above Earth, where the ISS orbits, gravity is almost as strong as it is here on the surface. The astronauts are not floating because gravity is gone. They are floating because they are in a continuous state of freefall. Let's break this myth carefully and understand why it's so powerful, why people believe it, and how the actual science behind it is even more fascinating. The images we see from space are incredibly persuasive. On Earth, gravity dominates everything we do. It keeps us grounded, pulls our dropped phone to the floor, and gives weight to every object we hold. So when we see astronauts weightless, our instinct is to assume that gravity simply stops working at high altitudes. After all, the farther you go from Earth, the weaker gravity becomes, right? That part is true, but not to the extent people imagine. At 400 kilometers above Earth, the force of gravity is still about 90% as strong as it is at sea level. In other words, if you weigh 60 kilograms on Earth, you'd still feel about 54 kilograms of gravitational pull at the height of the ISS. That's almost no difference. So clearly, astronauts are not weightless because gravity is missing. Here's the real magic. The ISS and everything inside it, including astronauts, are constantly falling toward Earth. But because the station is moving forward at nearly 28,000 kilometers per hour, it keeps missing Earth. Imagine throwing a ball forward. It curves downward as gravity pulls it. Now imagine throwing it so fast that the curve of its fall matches the curve of Earth itself. Instead of hitting the ground, it keeps falling around Earth forever. That's what orbit is, falling without ever landing. Astronauts inside the ISS are falling at the same rate as the station. Since both the station and its occupants are in free fall together, the astronauts feel weightless, not because gravity is absent, but because nothing is pushing back against them. On Earth, when you stand, the ground pushes upward on your feet, and that resistance is what gives you the sensation of weight. In orbit, that push disappears, and so does the feeling of weight. Think about a roller coaster when it suddenly drops. For a brief second, you feel your stomach float because both you and the seat are falling together. That's the exact same feeling astronauts have, except it lasts for months instead of seconds. NASA often uses the phrase microgravity to describe what astronauts experience. It doesn't mean zero gravity, but instead refers to the tiny variations in gravitational pull and the subtle forces inside the ISS. For example, the station is so large that different parts feel slightly different amounts of gravity. Movement inside, like astronauts pushing off walls, creates small accelerations. The pull of the moon and sun adds tiny effects too. So astronauts are never truly in zero gravity. They are in microgravity, a condition that mimics weightlessness because everything is falling together. The myth is not just harmless fun, it affects how we think about science. Understanding weightlessness is crucial for space exploration. Here are a few reasons. 1. Health risks for astronauts. Without gravity constantly pulling on their bodies, astronauts lose bone density, muscle strength, and even changes in eyesight. That's why they exercise for nearly 2 hours every day in space. 2. Scientific experiments. Scientists use microgravity to study things we can't test properly on Earth, like how flames behave without convection or how protein crystals form without the pull of gravity distorting them. Future of space travel. If we want humans to live on Mars or travel long distances, we must understand how microgravity affects the human body for years, not just months. Astronaut Don Pettit once explained it beautifully. We are not floating because there is no gravity. We are floating because we are falling. The Earth is pulling us just as hard as ever, but we are moving so fast sideways that the pull only curves our path, never lets us land. That simple explanation turns a confusing myth into a mind-blowing reality. Astronauts are not in a place without gravity. They are in a place where gravity becomes invisible. At first glance, no gravity in space sounds exciting, but the truth that astronauts are in a never-ending fall around the Earth is even more fascinating. It shows us that space travel is not about escaping Earth's forces, but about using them creatively. Next time someone says there's no gravity in space, you can tell them, actually, there's plenty of gravity. It's the reason astronauts are falling around Earth right now. This myth survives because images of astronauts floating are powerful, and the concept of weightlessness is counterintuitive. But the reality is rooted in orbital mechanics. Gravity is still very strong in space, and weightlessness comes from free fall. Far from being empty or boring, this truth reshapes how we think about physics, human health, and the future of space travel.